Next talk will be by Oleg on letter insertion without effects, light and magic. And I'm very curious to hear about that. So Oleg, the stage is yours.
Okay, thank you. So just to warn that I cannot actually see any questions or any, AirMeet main screen. I can only see my text. So if there is something, up and you have questions online, then please, let me know voice, because this is the only way I can be contacted. Okay, so the talk, as Jonathan said, letter insertion without effects, lights, and magic. And the most important part on this screen is in red. So the paper that was submitted, the extended version of the paper that was submitted, is now available on arXiv. So you don't have to, remember this URL. You just have to know that it is on arXiv. So the contents of the paper is, well, it's about let insertion. And also it talks about, it presents the first denotational semantics that treats not just let insertion, but also letrec and mutually letrec insertion. Because to our knowledge, letrec and letrec insertion has never been treated formally. And well, there's no continuation in state effect. Okay, the second point presents a little bit of a problem, actually quite a big problem for the presentation, because, well, this is a denotational semantics. And so in the paper, there are many equations that actually in symbols in 3 different fonts with subscripts and superscripts. So the challenge is how to present them to the audience. Well, of course, I can show them through several moments on the slides, but well, according to reviewers who, by their comments, spent quite a bit of time looking at the equations, that, they're not easily comprehensible, and they are asking that more intuition and more explanation is necessary. So I took the advice to the heart and set up myself a challenge. Can I explain the content of the paper and the main idea behind the denotational semantics without showing any single equation? Well, we shall see how that works out. So although the paper is theoretical and, as I said, lots of equations, that it isn't just a theory. Interestingly, that in the process of developing writing these equations, we came up with much simpler interface for mutual recursion that we had before, and also that guided the implementation in current MetaOCaml. So this is the, one of the interesting cases where theory actually, really went to the practice, and it actually very soon. Okay, so the talk is about the theme of the presentation is code generation. And one of the standard ways to do code generation is, well, using code templates. So code templates, for example, a string contains the code that we wanted to generate. It has some holes to be filled with some other code. For example, in this first line, we see the template is arithmetic expression, and it has holes like percent denoted by %s in which to plug some previously generated code. E1 and E2 is the two expressions standing for the code already generated, and n is presumably an integer. Well, if you come from a Lisp tradition, you probably would be more familiar with anti-quotation. So it's also the template, and the holes are denoted by unquotation. But there is a different way of generating code, and actually the one that we'll using this work and this paper and this presentation. It's code combinators, and it's actually a little bit more general way in the sense that oftentimes the previous way the templates are implemented in terms of code combinators. Well, code combinators is a combinator, so it means it's a function or closed term, and it produces code. Well, code is generally something like a string, but instead of string, I would write code because, well, to be more general, and also because it's shorter. And I also attach types because, well, it makes things a little bit easier to understand. So this is the same example that we saw before. So E1 and E2 are some early generated piece of code. Int is a code combinator because it returns code. So it takes integer and returns the code that contains the literal integer. And plus, its underline is once that takes two pieces of code and makes the piece of code that has an addition that contains the summing of those two previous pieces of code. And as a convention, all code combinators are underlined. Well, we can introduce a combinator lambda underscore, and if we do with this type, and if we do, we can generate functions. And so this is the way how lambda underscore is used. So that because the notation is a little bit heavier, I would simplify it a little bit as on the screen. This one. And this is the code which is supposed to be generated. So it generates the function. So assuming that the generated code is OCaml, and it could be roughly anything. Well, once we get into trouble of introducing lambda, we may as well introduce let, which is, if you look at the type, is very similar to lambda. And this is how that let combinator is supposed to be used, and this is the code it's supposed to generate. So this has been very straightforward, I hope. And it's very trivial, and actually very trivial. And let me point out the reason why it has been so trivial. So this step, the last example repeated. And I took the liberty also to introduce a few colored parentheses, and hopefully you see the different colors. So the point in here is how the structure of the generator expression, the generates code, matches the structure of the code which is generated. For example, that black parenthesis, so for my brown parenthesis, was the second child of the let combinator, let code combinator. And in the generated code, the code which generated by brown parenthesis is also the right child of the let expression. And also both black and brown parentheses are in the generator were sub-expressions of the red parentheses. And in the generated code is also the same. And this is, how the structures correspond. It's very, it makes it very easily to see what code is getting generated. And it's very also easy to give the semantics, and it's called compositionality. And this is all very great. Although if we look at the generated code, we see some not that great things. For example, we see this let y8 equal 1 plus 2. Well, 1 plus 2 doesn't actually, this is in the body of the function whose argument is x7, and it doesn't depend on the argument x7. So it just from the pure efficiency consideration, it would be actually nice if this let expression were somewhat higher, somewhat outside, because we don't have to recompute it every time we apply this function. So what we would like to have is a combinator which is called glet, with a type whose type looks, suspiciously like identity, which should work as shown on the slide. So the generated code, in the generated code, the let y equal y1 plus 2 would be completely outside of the body of the generated function. And that is, clearly the better way, more optimal way. So, which is, good. On the downside, if we look now at the structures, we see the structures no longer correspond. So, because the black parenthesis things used to be a sub-expression of the brown and the red parenthesis, and it's completely, outside of them in the generated code. So that, lack of the compositionality is, well, there is advantages, and then the biggest disadvantage is that it makes harder to make semantics and harder to understand. And this insertion, this, generating of this let, which is kind of outside of the expression, which is kind of higher in the, the code hierarchy, is called a let insertion. So that's the definition of let insertion, inserting let, and usually somewhere higher than, where glet appears. So the reason for introducing a let insertion has been to improve the performance. Well, there is another reason. And here, I mean, to illustrate, there is a little bit more complicated expression. So there is a let x, but this let x is not underlined. So it is the let in the generator, because there is a generator in 6 plus in 7, and it presumably appears twice in the generated code. And so we use let x to, abbreviate it and to share it. And as I said, the code is, as you see on the slide, contains 2 copies of the expression 6 plus 7 and 6 plus 7. And this is something that people a little bit may be surprised, especially the first time that come into code generation, because, they write the generator and there is a let expression. And when they see in the generated code, they see duplication and there is no sharing, there is no let expressions. Well, the answer is duh. Well, if you want to have let appeared in the generated code, then you have to use the let combinator that introduces this let. For example, let's use the combinator glet. So if we stick glet here, then we see that's the generated code. We see the generated code. And two things become clear from the code. So first is that why it's useful to push the let bindings as high as possible. Well, if the binding is as high as possible, then the the variable can be shared, can appear in many other expressions down below, as it is the case in the code. For example, x4 is, really very high, and so it appears in bodies of let x5 and let x6. So this is another, reason for let insertion and inserting higher than as high as possible. Also, non-compositionality is very glaring in this example, right? Because the code which is generated bears hardly any similarity to the code we started. So there is another way to look at the code, and this the code is the reason to look at the code is at the definitions is very well explained in this quotation from Principia Mathematica by Whitehead and Russell. So because let insertion is the way to introduce definitions in the code. And according to, as Whitehead and Russell say, on one hand, definitions are superfluous. It's just, essentially keyboard macros, just save us the typing. But on the other hand, they say that, it's often convey more important information than is contained in the proposition in which they're used. Because they embodies our choice of subject, because the structure of our presentation and contain the analysis of the whole idea. So one of the things is, is the word important, and then synonyms appear several times in the paragraph. So they certainly thought that definitions are important. Another thing to note is the word analysis. So the definition contains an analysis. Well, analysis is a thing that you have to do. And analysis is not often not clear from the onset. Well, which also goes very well with the importance, because what is important often is not clear from the beginning. And this leads to the following conclusions. So, of course, in the finished text, definitions have to precede uses. When we read, we first see the definition, and then we see when we read, we can refer to the symbol which was defined. But when we're writing, the use precedes the definition, because we don't actually, at the beginning when we started generating code, we don't even, we haven't performed analysis, so to speak. We don't actually know what is important. We don't even know what was to decide. Or to put it another way, so definitions are made in hindsight. So they read forwards, but generated backwards. And this is the reason that they're so difficult to uh, understand. And let me, harken back a little bit on this point. So suppose Russell, imagine Russell is typing Principia Mathematica. And so he comes upon the page which comes upon this writing a sentence that would definitely benefit from some definition. So what he should do? So he stands up from his desk. So he has to go back to the stack of already written pages, find the place to put the definition, writes the definition, returns to his desk, and resumes the writing, now using the thing he just defined. Or to put it a little bit, so what is this process is also very common, and it in a sense it appeared when I was editing or entering the text for this very slide for the presentation. So as you notice, well, of course I was using Beamer, and so I was writing the frame sharing, and so I wrote I wanted to use colored parentheses, and I entered this text color red parentheses. I look at this code and say, well, it's very, I don't know, well, it takes some space to write it, and I'm going to use it many times. So probably I should make a definition for it. So what I should do, so I go back to the beginning of the file where the definitions usually come up, find a place where the definition should go, insert the definition abbreviation, and then return to my text and enter the symbol I just defined. So this is step, as a matter of fact, I do it so often, so in my editor I have a special key that to go back to the place in which I edit. So I hope that you notice that I use the words back and forth and suspending and resuming. So that's what we have to do when we are writing code on writing text ourselves. But if we're building a generator, so the program that's going to do writing for us, so the program also needs to do some kind of going back and forth and suspending and resuming. So it needs facility such that coroutine, continuation passing style that lets it go back and forth or suspending and resuming. And this connection between let insertion and effects, such as coroutines, so delimited control effects, has been noticed long time ago, and lots of papers has been written by many people, including myself. So that's where effects come in. So seems to be a let insertion needs effects. Well, so it is, of course, very well known. And when we started writing denotation semantics, we kind of thought, well, it's kind of, we need to have denotations for effects, and this is getting too complicated. And maybe there is a simpler way of going about it. Well, so let me explain the idea. Unfortunately, my artistic skills failed me in writing, in creating good picture for that. But hopefully I can explain what I meant in words. So let's, going back to Russell writing writing Principia Mathematica and typing one page and coming across a point where he needs to notice something that benefits from the definition. Now, instead of, interrupting his work and standing up, he doesn't do anything. He takes pick up sticky notes, and on these notes writes what the definition should be and which symbol should be defined. And he sticks this note to the page and continue typing, now using the symbol just defined. When he finished the page, now he has to stand up and put it into the stack of already entered pages. So at this point, he takes the sticky notes and collects them and put into the stack of already written pages. Well, eventually he finishes the chapter. When he finishes the chapter, then, well, there is a sticky notes stuck on the beginning of the chapter. And in that case, at that time, he looks at the notes, and if the note says, the note seems to be that this is the definition should be inserted at the beginning of this chapter, then he inserts the definition, discards the notes, so actually makes real definition, and the remaining notes he sticks on the beginning of the whole book. And at the end, if there are some sticky notes left, then he makes the definitions right at the beginning of the book. So in this case, there is nothing going back and forth. There's just annotating. So we write a text, and if we need definition, we put this annotation right there. This is the symbol we just defined. The sticky notes, the annotations become the part of the code. So they go where the code is, they accompany the code, and when we take two expressions and combine them in a big expression, then we also merge the annotations. So in this case, there are no effects, as you can see. This is just collecting annotations. And that's the main idea. So if you understand this, then you can write a code and write the equations by yourself, very easily at a given time. Well, the paper, might save you time. So this explains most of the words in the title about definitions and effects and definitions and the lack of effects. And I think I have, almost hardly any time, right? Probably 5 minutes. So there is remaining parts is the parameterized definitions. So what do we do about recursive definitions? And here the example to describe it, it's Neil Jones' challenge of generating good code for Ackermann function, for specialized Ackermann function whose first argument is 2. So this is the real code, which which contains the partial application. Well, we can make it a generator just basically underlying everything except the variables. And this generates the code, which, we saw before, but this is probably not an optimal code. And the reason it's not optimal because, well, if we know that M is 2, that maybe we can take advantage of it. And this is a more advantageous code. So it's basically the same thing as that original code where some things are underlined. Well, because we want to generate function that takes n and computes the Ackermann to n, then at least n should be, the second lambda should be underlined, and the other underlining just follow from it. If we just do underlining and just do this underlining, that is, we don't get any code because, well, we could easily to see the whole thing diverges because Ackermann of 2 of M also depends on the Ackermann of M, and so the whole thing diverges. And by sticking at letrec, we make it we generate a code which also contains letrec, but this generated letrec have nothing to do with the ones, well, kind of very remotely have to do with the ones in the code. It seems that this kind of before used glet, and now it has gletrec. So it seems to be this is a quite a different and magical thing. But to our surprise, this is isn't a magical thing. It's just a very minor variation of the previous genlet. So it works exactly as before. So it creates the annotation. So gletrec, for example, in the expression that I'm showing, it creates the annotation for this application Ackermann M to for this invocation of Ackermann M. So it makes a code, chooses the name for the variables and puts the annotation. This is variable is should be defined by Ackermann M. And these annotations proliferate as before. The only thing is different that before we annotate, we bind, we defined a variable, a name, and already generated code. And here we, define a name and code, a generator. So not yet, a generated expression. But, the whole process is before. And it seems to be, I don't have, much time to, go further explaining it. So, but I gave the right, the main idea. So it looks like just a minor generation as before. So in conclusion, we saw that what let insertion actually means. So the best way to understand let insertion, we claim, is to think about definitions as a sticky notes, as a annotations to the code which we generated. And well, it's also fun to work out the equations, and the paper contains these equations, and also following this equation, all the code that I showed, they said, well, this is the code which is generated. We can compute that code which is supposed to be generated. And of course, computing and working out the equations is a little bit boring. So there is a code that, there is a program that works out equations for you and shows which code is generated. And as I said, that working on this equation showed how to simplify the interface for let-rec insertion and led to the implementation in current MetaOCaml. Well, thank you very much.
Thanks a lot, Oleg. We have one question in the Q&A tab, which is by Sam. And Sam is asking a question that I also wondered about. Surely taking notes is an effect, albeit a simpler one than delimited control. Do you have something to say about that?
Well, of course, when to have a conversation about effects, we need to define what effects is, right? And well, I myself, once argued that even, writing lambdas and even a variable reference is an effect. Upon this point of view, everything is effect. So what the claim is, and the paper has, the archive paper has a remark on this site. So the effects which people used for delimited control before were kind of, well, to say strong effect, like delimited control or state. And in the, well, I would say why is it strong is because they impose particular order of an evaluation. So you have expression E1 plus E2, then when you consider, like, for example, delimited control effects, you need to choose which expression to evaluate first. So it imposes some choice in evaluation order, or the state, for example. And if our, what semantics, which is, which we propose, has no, imposes per se, maybe other, difference between, or order evaluation between E1 and E2. Yeah,
so I seem to have been invited onto the stage. So right, maybe
yeah, so
clarify. Could I
say it again?
Can I follow up?
Yes. Yeah.
So is it right then that essentially what you're doing is, it's like a writer effect, the writer monad effect, something like that?
Well, no. Well, writer monad is the kind of a global state in which you write, right? And here is each expression has its own what you wrote to it. So it isn't, there isn't any global something that you write. And it's really, well, I skip for the sake of the time, then it really so if you duplicate the code, you duplicate the annotations, which is actually a very important point.
Right. So it's a bit more compositional than a writer.
Yes.
And I did have one other follow-up since I'm here, which is, are there any performance penalties due to using this approach rather than delimited control? Or have you compared performance?
Well, I would say performance winning.
Okay, right.
I think that's probably a better questions to ask.
And there aren't circumstances, I don't know, like when you start using sums and things where by which I mean coproducts, as in types, where that you start to lose the performance gains.
No, well, it's actually the other way around, because originally MetaOCaml used had to use delimited control to introduce let, right? And well, delimited control is a heavy thing because, well, copying things stay, a stack and so forth, so forth. So it's really heavy thing. So, and it turns out, well, MetaOCaml already for the point of, speaking to the paper that will be, has been already presented by Bridget Pienka. It's in a sense, it's a contextual model type theory, but it's not a type, but there is a code is annotated with free variables. And MetaOCaml already had this, the whole infrastructure, because it's needed for scope exclusion. And when I noticed that this let insertion just a minor variation of this infrastructure that I already had. So just add, I think I added maybe 20 lines of code. Adding 20 lines of code to existing interpreter, I can do exactly what I had with delimited control, but without delimited control. So it actually net win.
In the interest of time, maybe Ohad can briefly ask a question, but I'm not sure whether we need to leave this session or take it offline. I'm not sure. But Ohad, you have a short question?
Am I audible? Oh, yes, I am. Okay.
Yes,
I was just following up from Sam. It looks like the effect here is, read-only full-ground state. So you can dynamically allocate new read-only cells, and those cells can point to other cells. And that's going to be conjecture. I haven't proved this. Commutative, and so you can reorder them so long as you respect the dependencies, and so on. So I am seeing an effect here, like Sam says, but it is much simpler.
The read-only component seems important here, yes?
Yeah.
Okay, then thanks for your question. Thanks, Oleg, again for your interesting talk and for insights on Russell's writing process. And yes, please, let's thank the speaker again.
Okay, thank you.